Um, Hello, everyone. I'm Xinyu from UCSD EC department. I'm going to introduce in a little bit of more detail about our 5G testbed. From our previous talks, you have already seen 5G will bring a lot of new, exciting applications to our life. And one particular set of interesting applications is connected vehicles enabled by the Vehicular to Everything 5G communications, or V2X. Examples including camera view sharing between vehicles, sensor data sharing, mobile edge computing for machine vision applications, and also new generation of in-vehicle entertainment systems. All of this will depend on a few core features of 5G, including ultra high bandwidth brought about by millimeter wave and ultra low latency, as well as mobile edge computing and software defined core networking. So all of these capabilities up to now are still within the paperwork and stay on the concept level. At UCSD in CWC, we're trying to build an experimental testbed to really explore all of these 5G features as well as applications and try to debug the problems before the problems actually occur in our actual 5G network. Here's then a very high-level overview of the testbed. Essentially, we're going to deploy 5G base stations on top of roofs and also on street lights. These base stations will have millimeter wave communication capabilities as well as the sub-6 gigahertz communication modules. And between the base stations, we can use the high bandwidth wireless backhaul to establish very lightweight communication capabilities at high bandwidth. Between the base stations and the vehicles, we can either use directional millimeter wave or the sub-6 gigahertz microwave band for communication purposes. And there will be a control center. You can think about it as running the core network management as well as the software-defined services. Let me get into a little bit of more detail about each of the components. As I mentioned, the base stations will have both millimeter wave and sub-6 gigahertz modules. And this is showing our base station, which has a millimeter wave radio inside it. This millimeter wave radio has 8 phase array antennas, able to send the beams towards many hundreds of different directions with hundreds of antenna elements. And this platform, this radio was actually adapted from a company called Airfied, which is using Qualcomm's latest millimeter wave chipset. We also have programmable sub-6 gigahertz base stations. This base station is built on NI USRP N310 software radio. You can program it into a LTE base station, and you can also upgrade it to a 5G base station as well. And you can essentially implement anything you want from the physical layer signal processing all the way up to mobile applications. Co-located with each base station is a mobile edge server, which is going to run some machine vision or other kinds of 5G applications. The UE, the user equipment, can be either a vehicle, a drone, or a user carrying the 5G device. Right now, we have both millimeter wave radio with a phased array antenna, as well as a sub-6 gigahertz programmable radio. Both of them are able to run as the user equipment under mobile conditions. Let me show you some very small benchmark tests that we have done to essentially demonstrate our deployment. This is one deployment of a sub-6 gigahertz base station, which is placed on top of the Atkinson Hall. There's also a mobile user equipment mounted on top of a car running inside the parking lot near the Atkinson Hall. And this heat map is essentially showing the signal to noise ratio that we measured as we drive around this area. You can see that for most of the locations, the signal to noise ratio is at a high level, but there are also some blind spots showing the lack of coverage due to, for example, tree blockage and other problems like fading. This video is actually a real-time video that we are streaming from the mobile edge server co-located with the base station to the mobile user equipment on the car. Besides the video application, we can also see the actual signals being sent from the base station. We can see the constellation diagram, essentially evaluate the signal quality and look at the detailed channel state information. Essentially, this gives us full stack information about the entire network. This is another test case where we are evaluating a collaborative contextual awareness application. Here, a drone is flying in the air at the corner of a street, trying to capture a broader view of the environment. And the drone is sending the real-time camera video to a mobile edge server co-located with the base station. And the mobile edge server is running some object detection application, machine vision application. And then further, it will deliver the detected result to a mobile UE, which is inside a car. This video is the view of the car, essentially what it sees after it gets the data from the base station. You can see that roughly the people walking around as well as the vehicles are being detected accurately. So this is just a very microscopic view of what we can do, but there's a lot we can build on top of this test bed. As I mentioned, this test bed will enable us to do full stack 5G research. We can answer questions such as, can we enable seamless gigabps connectivity using 5G million per wave? And can we enable machine learning driven mobile core networks? And can we enable self-driving cars for the dumb cars as well, not just the smart cars, but relying on the 5G communication capabilities? One benchmark project that we have been working on recently is trying to realize seamless connectivity or omni-directional coverage for 5G millimeter wave networks. You probably had heard about the limitations of millimeter wave. Many people are saying that because millimeter wave radios are using highly directional beams for communication purposes, so they think it's just like laser. You're never going to achieve as good coverage as the traditional cellular network. Not just that, besides the directionality, there's also the so-called field of view problem. Each millimeter wave radio has a very limited field of view within certain angle. As we measured based on off-the-shelf millimeter wave radio, we saw that even if the radio can steer the beam in real time towards many directions, its maximum field of view is always limited to, for example, 120 degrees or 90 degrees. And within the field of view, you can achieve very high throughput. Suppose you can steer the beam in the correct way. But out of the field of view, the throughput is much lower. It can barely support any connectivity. So one way to solve this problem we thought about is we can actually put multiple phase arrays together facing different directions to form an array of phase arrays, just like this, 4 phase array antennas facing different directions, and each phase array can have hundreds of different beams steering in the 3D space to make sure that there's always coverage towards any spots. We call this setup X array to just referring to the array of phase arrays setup. So the high-level idea is simple, but in order to really make this work to achieve full coverage, we have to solve a lot of core challenges. For example, which phase arrays should we turn on? And within each phase array, which beam should we turn on? We have to make these decisions in real time, and we have to make sure the decision is correct. We have to make sure the decision overhead is minimum. Otherwise, we will waste most of our time just doing trial and error beam steering rather than useful data transmission. Our team has addressed these problems by designing some intelligent beam management and also array management algorithms. So from a very high level, the basic idea is that we can use some low-level information about the channel state to roughly estimate the angular, the relative angle between the base station and the UE with almost negligible overhead. And we can keep track of the angle so that we know which phase array we should turn on that faces the angular direction of the UE, and which beam should we trigger on that phase array. And simultaneously, we can decide on whether we should turn on multiple phase arrays to maximize the joint power at the UE side. We found that we can actually configure the phase offset between two phase arrays so that we can make sure their signals can coherently combine with each other to achieve the maximum power. Our measurement studies showed that by doing this kind of co-phasing or so-called dynamic pre-coding, we can achieve more than 10 dB of received signal strength improvement compared with the brute force way of directly triggering the two phase arrays, but without co-phasing. We have implemented this entire X-array system on our testbed. Again, the base station is a multi-array system. Originally, this system wasn't intended for X-array. It was actually 8 phase arrays facing the same direction, but our student did some 3D printing mounting kit to retrofit this entire system so that we can let it become X-array. And among these 8 phase arrays, each of them will have 36 antenna elements, able to generate 64 different beam directions. And each phase array has a co-located controller box with a Raspberry Pi running LT. And there's also a battery storing some power. This entire system is actually running independent of the power line because we are actually using solar power to charge this battery to drive this entire base station, millimeter wave base station. And the control logic that I mentioned is implemented actually in a separate controller running in the cloud. You can essentially think about this as a software-defined wireless network, where the key decision about the network is actually made in the cloud through a low-rate control channel, actually LTE control channel. But the actual data transmission is done by the radio access network, by the millimeter wave network. This control flow is a bit complicated, but this is basically following what I mentioned in discussing about the control logic. Essentially, we need to choose the best phase arrays to turn on, as well as the best beams to turn on in real time. So we have some quantitative results, but here I'm just going to show you some very intuitive demonstration of how well this system works. We had both indoor and outdoor experiments. This is an indoor experiment where we are walking around the base station. And meanwhile, we are measuring what are the phase arrays being turned on and also what are the best beams being turned on as we walk around. And our results demonstrate that the best beams as well as the best phase arrays are roughly following the ground truth, the Oracle best choice. And we can consistently maintain high signal to noise ratio as we walk around the base station. We have also done outdoor tests within the parking lot. Again, this is demonstrating that as the car moves around, the multiple phase arrays are turned on simultaneously, pointing to the UE's direction and maintain a very high signal to noise ratio. To briefly summarize, we already know that 5G is going to bring new exciting use cases to connected vehicles. And here we are adopting an experiment-driven approach to explore many of the features and problems in 5G V2X. And our recent research focuses on deploying a campus-wide testbed based on 5G millimeter wave as well as sub-6 gigahertz. Because of the programmability of this testbed, we imagine that we can do full stack research on 5G systems from communications all the way up to mobile applications. Thank you. Any questions?
I may not be super familiar with this, but how does the difference between millimeter wave and 5G work with V2X being a protocol that's supposed to be standardized between multiple different companies and products and vehicles and that sort of thing?
Millimeter wave is just one component within 5G. 5G supports both the millimeter wave frequency as well as the low frequency, which is the so-called microwave. These are just different kinds of radio signals with different propagation features and different speed.
I see. So let's say that for like a vehicle, like a car, so a vehicle that supports 5G V2X would be required to have sensors for all these different types of protocols?
Suppose the vehicle is going to use millimeter wave, then it has to have a millimeter wave radio. And if it's going to use the sub 6 gigahertz, it's going to have a sub 6 gigahertz radio as well. But we can imagine that in future, we can use, for example, our 5G phones inside cars as a communication module as well. And the 5G phones will also have both millimeter wave and sub 6 gigahertz modules.
Thank you.
Thanks.
Also mention that you heard from the previous discussions DSRC, V2V, V2X. So V2X is typically assuming LTE bands, sub 6 gigahertz bands. And that the reason being, I think that millimeter wave has not been proven yet in the outdoor, especially in this kind of very, very wild outdoor vehicular kind of situation. And so this is where we are leading in the research. And if our research goes well, hopefully our partner companies will be putting in millimeter wave into the V2X standards also.
Yes. Another question?
I mean, when you go to millimeter wave, I suspect you may get some scattering off of adjacent cars in the parking lot and so forth. Does your algorithm, let's say, can handle the jumps that you might have with the multipath, particularly with the beam coordination when you have two sectors following the car?
That's right. We do have some design to handle multipath as well as blockage. Actually, under this kind of situations, we will just trigger kind of emergency response to more intelligently scan a few phase array antennas so that we can figure out what's the best alternative rather than using the line of sight.
Thank you.
Thanks. We can. Thank you. So next one will be Marco.